I think we can start by saying good morning to everybody. It gives me great pleasure to introduce Professor Gehan Amaratunga from Cambridge University. I met Gehan many years ago when I did my sabbatical there. And before we proceed, I want to thank you for coming and let you know that there's two people that would like to be here, but couldn't be here. Sasantha Mitra is one of them, the director of the Waterloo Institute for Nanotechnology, because currently I believe in Asia, and Lisa Prokryets, who is running a lot of behind the scenes thing, that she's in Europe. So we're kind of traveling all over, and great pleasure to have Gehan here. I got his CV, and it's 10 miles long. Okay, 9.5, whatever, but Gehan, could you please come and tell us the great things that you're doing at Cambridge University and prove to us how we should feel great for having you here.
Okay.
Okay. He said, don't read this.
Yeah.
Thank you.
Yeah. So, thank you very much for inviting me to come to Waterloo and to share some of the work which I've been involved in the last maybe 5 or 6 years. 2015. So my talk is called Quantum Dots to Light. And I'll start off by introducing quantum dots and why they're interesting. Excuse me for the people who are very familiar with this, but since this is a broad audience and includes some students, I thought I'll go through the fundamental thing about quantum dots. Essentially it's a structure, if you look at the electronic bands, between a bulk material and a molecule. So you can take a molecule of the material, let's say silicon even, the energy states are well defined. And when you go to bulk silicon, you get a band structure, and you get something in between, what we call a quantum dot. And there, essentially, you get energy states which are discretized, and they're discretized and they remain discretized, unlike in a band, because we made it small. And the back of the envelope calculation you can do is just start from the Heisenberg uncertainty principle and work out that there's an energy of confinement, which is the uncertainty, which must be at least bigger than the uncertainty in the momentum, squared divided by m, of course, that's energy. And that's related by Heisenberg uncertainty to h bar squared 2m over delta x. And then we just rearrange this, okay? And you get this E confinement must be, approximately this much, and that must be larger than the thermal energy, which you can get from the environment to do that for a transition between the energy states. Okay, so it's very simple. As long as this confined energy is larger than the thermal energy, then you get these discretized energy states for electrons in the equivalent of the valence band, or the occupied molecular states, if you want to look at it that way. And if you look at the delta X, therefore, you get a size effect when this happens, which is, delta X roughly about, actually, I can use the pointer here, maybe. It's maybe better. Yeah, so it turns out that, if delta X is smaller than 10 nanometers, as is in one dimension, you can have these discretization of the energy states. Now, in a quantum dot, you do this in 3 dimensions. It's a particle, and the particle size is smaller than 10 nanometers. So why is this interesting? It's interesting because essentially you can make any semiconducting material, I'm talking about semiconductors here, essentially a direct bandgap semiconductor, because you break the rules of having a lattice, like in the bulk. It becomes molecular-like in the way it emits light. So if you take a molecule, it can absorb light and have a transition between energy states. And when the excited state decays, it emits light. You can have a similar molecular structure, but in a particle in 3 dimensions. And this gap, as I will show you later, is directly related to the size. So by making the size different, you can change this energy gap. And if you absorb light, it goes to a higher state, and then it decays to the lowest possible energy state in the conduction band equivalent, or in a molecule the lowest unoccupied molecular orbital, the LUMO level, and then it decays to the HOMO level. So it then becomes like a direct bandgap semiconductor. If you take gallium arsenide, it's a direct bandgap semiconductor, very good for light because in a direct transition, it's only energy, absorbs energy, and then can emit energy, light, without having to have an interaction with the lattice, with the phonon and the phonon dynamics. But we can take any material and make it a pseudo direct bandgap material in terms of a semiconductor for light emission. So that's why quantum dots are, very interesting for light emission, and I hope you share my enthusiasm at the end of the talk. Okay, so a quantum dot essentially is look at the scale by its 2 nanometers, roughly 10 nanometers across, and you get a physical structure which is a dot. But this is not, but that's the idealized case, because the problem with these nanostructures is you get a surface, and the surface to volume area in a nanostructure is very high compared to a bulk material where the surface just ends at one level, but it is covered by surface, and the surface is extremely reactive, okay, because you've got unsatisfied bonds, because you're essentially breaking a 3D order on a surface, and you've got these unsatisfied bonds, and these unsatisfied bonds are very reactive, and they're defect states. Then you get defect states which appear in the band gap, and the whole lovely idea of using these things as pure light emitters, you lose. So you have to passivate the surface in order to use this as a quantum dot. And so to that, we use some other material, which is a wider gap material, typically zinc sulfide or some 2,6 type material. But then also you've got to stop them from agglomerating. Okay, so to stop them from agglomerating, this is all chemistry, you have to have some surface ligands which essentially keep them apart. Okay, so the surface ligands act as, if you like, electrostatic repelling agents in a liquid, for example, and then you can keep these quantum dots in a liquid. Let's say we start in a liquid, and you keep them apart without agglomerating. And in that situation, what you find is, and this is it is cadmium sulfide, cadmium selenide, and as the dot gets smaller and smaller, the energy gap gets larger and larger. And if you have these in a solution, I will go into the solution, say a hexane or some organic solution, and you shine UV light, then depending on the size, this minimum gap becomes either red, yellow, green, blue, or turquoise blue, right? Just by size. And you can see the size goes from about 6 nanometers to 2 nanometers in this case here. So you get, this is down conversion, but it's photoluminescent. Now, in nanotechnology, those of you who've done nanotechnology might have seen some similar color variation. People who put silver nanoparticles, and say silver nanoparticles, depending on the size, also have different colors. But that's a different mechanism. That's surface plasmon resonance. And that's, I won't go into that, but that's a different mechanism. It's a metal, and the surface plasmon, the electrons oscillate at a certain frequency, can also give out light. But here I'm talking about semiconducting quantum dots. Now, a fascinating thing to think about is that the light emitted is the wavelength range, visible range, which is hundreds of nanometers. The particle itself is 2 orders of magnitude smaller. So the particle is, 2 orders of magnitude smaller than the actual wavelength of the light. But energy-wise, we can get light emission. So a nanostructure can absorb and emit light, which is it's 100 times larger than its wavelength. So that's one of the key, fascinating discoveries that was made at the inception of what we call nanotechnology, perhaps 30 years ago, right? So these nanoparticles can be very good light emitters, and this sort of the whole idea of nanophotonics starts from there. Now, why is it good for this type of light emission? So why, okay, so you can get others. So let's go here. So that's a dye molecule, a cyan dye. So now, of course, for light emission, you can have dyes, chemical dyes, coloring agents for many things. Then what you see is that it'll absorb light and emit light at a very close energy. So it absorbs light. If you have a blue dye, or in this case, they absorb light in the blue and emit light in the blue. So the absorption and emission is very close together. So a dye works by taking white light, absorbs the blue, and re-emits the blue. Okay. Now, if you go to the top here, you look at a quantum dot, the absorption is these lines here, and the coloring reflects the size. Okay, so it absorbs light in the UV, but emits in the visible. So there's a big shift from the absorption edge to the emission edge, which means that for photoluminescent down conversion, this is ideal. So I can blast a very high energy light, say UV light, and then I can choose the emission which I want just based on size, which you cannot do with a molecular dye. Okay, so and you can see this is what's called the Stokes shift is very large, and hence for this photoluminescent light conversion or down conversion, this is very it's like a very interesting material. And this is in different liquids, the colloids. These are colloids of quantum dots. And of course, the excess energy of the light, which is non-emitted, has to be transferred as heat to the liquid that it's in. So there's an interaction with the solution as well as the light absorption and emission, which one needs to think about. Okay, but these are very nice, fine, sharp emission of light. And I'll go towards the show that this has been used to get very pure blue, green, and red emitters for LCD lights or LEDs, and these can be give very sharp displays of just an image of a LED display where you're using quantum dots as the light emitters. In this case, the backlight shines on quantum dots of different size, and essentially you have a liquid crystal in a display. I'll come back to that, where you switch which ones you turn on. Okay, so that's the basis of the quantum dot and why it's interesting for light emission. So if we just look at it, what the chemistry of this is, I'm an electrical engineer, so I don't do the synthesis. I have my colleagues who synthesize all this. And the chemistry is, actually it's quite complex. I'm interested in using it for applications, but there's the core. Then the core has to be matched with the shell, as I said, for the surface passivation. And then you have to have a organic ligand, which also acts as a surface defect passivation on the second layer. Okay, so that's quite a complex chemistry and colloidal chemistry to make these quantum dots. And this has been mastered over the last 10, 15 years. And if you look at, just to emphasize the point, if I take cadmium selenide in bulk will emit at 1.2 microns, it's invisible. Okay? But by changing its size, we can get this whole spectrum of colors by going from small to large and shining light, and you can see that's there. So this goes back to 1993, so that's exactly about 30 years ago, where people started exploring these structures, or noticed that we could do this with quantum dots. Okay. Then I'll jump forward to an application straight away where we're going, but we can get this excellent color gamut, narrow emission. So if you look blue, green, red, the narrow lines are quantum dots, and the wider emission is from a phosphor. So what do you use? Typically, if you use the phosphor, you do the same thing. You can get down conversion in some molecules within a phosphor, but it's not as pure in terms of the emission spectrum as you can get from a quantum dot. Okay. Now, the first application of this, and remember that this whole color gamut in theory is available, is to replace the phosphor in a backlight. Okay. The first, most probably going back about, I suppose, 7-8 years ago, you saw that there were these, Samsung and what they call an LED display. Okay, so that LED display was a LED backlight on a liquid crystal display. Okay, QLED they called it, and this is what was happening there. They use a blue laser or a UV laser LED as the blue light source. Okay, for the white light, remember, and then they put red and green quantum dots in a matrix through which the blue is emitted. But since there are quantum dots, there's a down conversion of the blue into red and green as well, as you can see in this picture here. Okay, so this is the UV. You can have the red and green, or you can have the blue as well, and you get some emission, and you get a combined emission. If you tune it, you're going to get a very pure white light. Okay, and we'll see why I'm concentrating on the white light right at the start when I come to the end of my talk. So this backlight, the white light, it was the first application of these quantum dots. Okay, now these materials, which I talked about before, cadmium. So the problem is cadmium is a heavy metal. So a lot of chemistry which has gone on is to look at non-heavy metal quantum dots. One material is indium phosphide, which is can be also used with a passivation layer of zinc selenide sulfide. But here is a problem. We think the photoluminescent quantum yield, that is the number of photons emitted to the number of photons absorbed, the efficiency of that. In the red, it's about 82%. In the green, it's 80%. But when it goes to the blue, the efficiency drops significantly. So in quantum dots, the blue emitter is not so efficient for this photoluminescent quantum yield. So that's an issue, but it's not a showstopper. And the other quaternary material, which is also being explored, is copper, indium, zinc sulfide. And that too, you can see that in the red and the green, the photoluminescent quantum yield is pretty good. But again, when we go to the blue, it's not good. But we can have non-heavy metal quantum dots as well, which is currently what people are exploring in the research space. Okay, so this is the white light, very bright white light, and let me explain how this works again, just from sort of an engineering perspective. You have a sharp white light. Okay, so you have, instead of having a fluorescent white light, as what they used to have in LCD displays, you have bright white LEDs, and these white LEDs go through a plane, a liquid crystal plane, where the liquid crystal, depending on its orientation, switches the light through, or it stops it going. Okay, and then in front of it, you get a red filter, a blue filter, a red filter, green filter, and a blue filter. Okay, so the white light that comes through gets filtered either green, blue, or red, depending on the switching of the liquid crystal. But the primary light source is this white LED light, which is made this way. Okay, so with a blue or a blue LED, gallium nitride, and these quantum dots, which are red and green. And so that's the white light, and what comes out is the filtered light, which is RGB. Now with this, you can see it's first reported in 2010, and in 2015, Samsung brought out this backlight unit, the quantum dot backlight unit LCD TV. This is a 46-inch, and you can see that the color, depending on the fluorescent backlight versus the QD backlight, the display becomes better, sharper, and the color quality becomes nicer. So this is the one of the applications of quantum or nanotechnology for light emission in which you can experience every day now, because most displays are still LCD displays with these quantum dot backlights. And this is from LG and Sony. Similarly, this is the quantum dot backlight unit, and this is the if you just have a LED backlight unit, just the LED backlight unit is a blue LED, and two phosphors, which will down convert into blue and green. Okay, so you can see that the quality is very good. Now, my interest is not in that type of display, but is to make a full quantum dot LED, a light emitting diode. There, instead of having a light source which is down converted, we apply a voltage, and like an LED, we pump electrons into the quantum dot system, have excess electrons, excess holes, and they recombine. And they recombine in the between the lowest energy level in the conduction band equivalent and the highest energy level in the valence band equivalent, which we determine by the size of the quantum dot. So if you look at it here, there is a layer by changing the voltage. If I take this positive, I make holes come through, and the whole transport goes through some energy levels, whole transport layer. This is negative, so we pump electrons through electron transport layer. They enter the quantum dot layer, and you get light coming out. Okay, so we can go, instead of having light to light, we can go from electricity or electrical current to light, okay, which is what a LED is. Okay, so now a quantum dot EL display was displayed by Samsung again, and my colleague Don Kim worked on this at Samsung, and I also was a collaborator with him in this process. And in Nature, Photonics, we published in 2009 this one of the first quantum dot displays, relatively small, but this is basically an LED quantum dot display where we are getting blue, green, and red, all from quantum dots. Now, what I showed you was the end result, which got into Nature. But to get to that, you have to create a whole new technology. And I just want to emphasize this, that that the theory is great and the concepts can be proven, but to create a technology, you have to actually invent some new things. And what they invented at Samsung was a method of dry printing quantum dots, monolayer quantum dots. And the technique is this. First of all, you have a base holder which has some a SAM layer, some Langmuir-Blodgett film, which means that the quantum dots attach and get stuck onto it, but it's in a monolayer, okay, on a holder. And onto this monolayer, you bring a stamp, a PDMS stamp. You stamp it, and you transfer onto the stamp where the protrusions are quantum dots from this holder layer. Then you take it and you stamp it on the substrate where you want it, and you get these layers of a different color. So you do that with red quantum dots, green quantum dots, and blue quantum dots, and you can make monolayer quantum dots in patterns of microns for pixel sizes which you require for a display. But for this whole process, there's a whole lot of research done on the kinetic control of adhesion from stamping, transfer, and successful transfer. I mean, the amount of, I think, man hours that went into that whole effort of doing this transfer printing of quantum dots is really very significant. So I don't want to in any way downplay the engineering which enables us to explore and to utilize these ideas. And this is essentially the strength of big research groups, industrial research companies like Samsung, Sony, LG, these companies, which at universities we don't we don't have the resources nor the range of skills which are focused on one problem to solve these technological problems. But once they're solved, of course, we can all use them. Now, our work at Cambridge started when about 2013, 14, about 10 years ago, again in collaboration with my colleague John Ming Kim, who was at Samsung, and then he left and he went to Oxford, and we started collaborating, and then he came to Cambridge in 2015. And then we have a simpler, relatively simple, okay, this is the light emitting diodes structure. Again, the whole transport layer is quite complex, and there are these number of layers which you need to think about, okay? So not just the quantum dot layer, you need to think about a whole stack of materials. And then you can get red, green, blue emitters. Okay, so that's a starting point. We can make quantum dot LEDs. Now, where do we go from there? Okay, so my particular interest has been on lighting, this type of lighting, which is based on quantum dot LEDs. So you know that there are LED lights already. Maybe some of these are LEDs, these are not, but we all have LED lights. But how does the LED light work? Well, the LED white light works by essentially you have an LED, which is actually a UV LED, and then it hits a phosphor. If you look at an LED light, you'll see there's a dome, little white dome. That white dome is just a phosphor. The LED, what you're seeing is not the LED light. You're seeing the light which is being emitted from a phosphor. Okay? Now, what we want to try to do is to have red, green, blue LEDs, and with the red, green, blue LEDs, get a pure LED light, because we can do RGB in the LED space. Okay? Now, why do we want to do that? Well, when you talk about white light, there are many whites. Okay? So you already know that most probably this warm, what they call warm white, people have that in the night. But quite a lot of the time, what you have is this blue, which is most office environments and factory environments, you're there, and at home you're in there. But there's this whole spectrum of white light, which should be accessed, okay, from warm light to cool light. So how could we try to do this? So we could do this, a simpler structure, one hole transport layer, one electron transport layer, indium tin oxide, which is a transparent conductor. So there's glass on this side, aluminum on this side. That's the contact. And we inject electrons, inject holes, and they recombine. And they recombine, it can be in a combined RGB layer of quantum dots. But of course, the emission of the blue is much less efficient than the R and the red and the green. So that means you got to have some design criteria on how to get white out of a combined layer, okay? Or say even a striped layer. Now, if you just make in this ratio, red 1, green 1.6, blue 16, because of the emission efficiency drop in the blue, the content has to be higher, and we can get a light. But it's in the color spectrum, we're in this area here, okay, cool white, or the high color temperature. Now, by adjusting this, and this is made up of, this is the blue, this is the green, and this is the red band. You can see the blue band is high. So most probably we've gone too high on the 16 there, okay? Now we can change the ratio, 1, 2 to 9, and we can access a white which goes across a number of whites by changing the voltage of the LED. By changing the voltage, that means you're changing the amount of electrons to hole ratios which you're pumping into the LED, which in turn allows you to access a wider spectrum of light along the where we want to be, along the white hue range. Okay, that's 1.229. But this is all a little bit cumbersome, isn't it? I mean, it's all empirical. How do we do this? How do we get a light? How do we go about doing this? And then we can ask the question, actually, why do we need to just limit ourselves to RGB? I mean, this goes back to Thomas Young, who said that the eye has three nodes, sensitive nodes, which is red, green, blue, and therefore everybody goes with red, green, blue. But there's a thing called metamermism, which means that actually with different light spectra, we can see the same color. It doesn't have to be RGB, it can be shades of red, green, and blue, and you can change this and you can get different, the same thing. There's massive redundancy in terms of the primaries that you can use for human vision. Now, doing that, you can also do some clever things. Like if you think about the power that's required, and this is standard LEDs, this is 3.5 LEDs, you see that the least efficient, the radiation flux is lowest when you come to this green region here. Okay, this is the blue, this is the green, and this is the red. So, why don't we try to make this peak with something here and something here, for example, put 4 primaries instead of 3 and get high efficiency. That's a possibility, right? And so what we did was leverage this metamermism by just saying we have quantum dots, we have more than one primary, we can have a combination of primaries, and say if I had to access a point here on the color spectrum, well, I could have primaries in all these white spaces. White dots could be all primaries. And if I put these 3, I can access this space. I can put these 3 and access the same point on the color space. Okay? And you can do some optimization depending on power or brightness or something else in real time and make the light smart. Okay? So that's one possibility that you start to look at. And in applications to lighting, this allows us to create arbitral spectral shapes of quantum dots with multi-primary architecture. But the massive redundancy means there's an information optimization exercise which has to be taken. So we applied some techniques from, I don't want to make it sound too what shall I say, too fashionable and say we applied AI for this. I wouldn't say AI, we applied some machine learning type knowledge to try to optimize what the spectrum of primaries should be. And what we found was that with 4 primaries, introducing one more, you can see that there's this turquoise one. We can get a color rendering index that's a standard for lighting, the color rendering for different colors, how well it is reproduced. That is, if you put a color palette under this light, what you see and the color purity you see is called a color rendering index, because the white light has to reflect dyes and other lights in a way which has got high fidelity. And with 4 primaries, we can get a fidelity which is good enough, nearly 90%, and going to 5 and 6 primaries, doesn't give us that much advantage. Okay, so going from 3 to 4 makes a significant difference in the color rendering index. Okay, with only four primaries. So that we do with some sort of calculation and mathematics, and that mathematics involved modeling, because we had to model how much light would be emitted at a certain current. Okay, and the modeling aspect is again not not trivial because you're trying to model the recombination of electrons and holes in a quantum dot, but the electrons and the holes have to travel through the quantum dot. And the electron transport mechanism and the hole transport mechanism in quantum dots with their surfaces and surface interactions is unknown. So we had to develop some model. We had a team of people who developed the modeling by having a semiconductor model which is modified with some quantum dot parameters, and you can see, depending on the voltage you apply, then you can see the hole and electron concentration in the quantum dot layer, from which you can then get the emission characteristic. So this is the emission characteristic if you have stripes of equal width, but if you change the width, obviously the blue will be larger width because it is less efficient, then you can get a different spectrum. Okay, so with this, through the modeling, we can see, this is the color rendering index, which I just showed. These are the colors that you have to render for the standard. And you can see that the CIE standard is somewhere here. And then we can get it somewhere here. So we're close to the CIE standard with the 4 primaries, and you can access this color range over here. Okay, so this goes to red, green, cyan, and blue. So instead of pure red, green, blue, we adjusted the color spectrum to 4 primaries. And this shows the variation of the current density that we measure in the diodes for the different colors with applied voltage, the external quantum efficiency, that is the number of electrons current to photons emitted, and with voltage and with current, this is the measured and this is the modeled. Okay, so that allows us to actually go about doing some design of a white light and optimal white light, because we've got a match between some modeling capability and physically what's happening in the quantum dot layers in an LED. And with that, what I show you is, this is the color temperature chart, okay, which can go from 3 volts to 5 volts to 7 volts. And you can see that we can access this entire range of white hues in one light by changing the voltage. Okay? If we had identical stripes, then we can only access this range by changing voltage. By doing our design, by optimizing the quantum dot structure, mainly the stripe widths, relative stripe widths, we can have access through our modeling and optimization, you can access this entire spectrum of white light. Okay. And the color rendering temperature is 92%. This is, it goes from 1,600 Kelvin to 8,000, nearly 9,000 Kelvin. That's the widest color range, color temperature range you can get from one light. From one light, the widest color temperature range you can get at present is this. Now, Philips, I mean, good ideas aren't exclusive, right? If you're having a good idea, somebody else is already having the same idea somewhere else. So Philips, mega corporation, has the same idea. They also want to make this, and Philips have a thing called a smart light. Their smart light, however, introduces into this green cyan band, they introduce a phosphor. It's not only LED. So they have a red LED, a green LED, and then they put a phosphor, which down converts the blue into this range here, similarly. But their color range is not as good. Okay, they're of course a mega corporation, and their lights are, they're available. You can buy, I don't know whether you can buy them in Canada, but in Europe you can buy a smart, it's called a smart light from Philips. Okay, but that's what they do, but the color range is not as good. So this work we published in a range of articles. And I want to say that, this has all been possible mainly of, okay, the idea of the smart white light is, we contributed, but a lot of the technology we have at Cambridge came when Yeonmin Kim joined us from Samsung by Oxford. And he built up a lab which has transfer printing and ability for us to explore these ideas. Now, okay, so why do we need this type of color spectrum? I mean, so we can do it, but is it important? What's the point of it? Well, the point of it is this, actually. The impact of light on human health and well-being. It's only just now starting to be understood more. Now, you may have all heard of the circadian rhythm, right? The body function is related to a cycle, a daylight cycle. All right? And that's been shown, and there's a review article, if I put there, sleep, circadian rhythms, and health. Okay? So we know that the circadian rhythm has an impact on our health. That's the white light cycle that we see. And that's also for plants, this is true, and for many biological entities, this is geared to, their function is geared towards the daylight cycle. Okay, and the daylight cycle is not one spectrum of white light, okay, but rather a gamut of white lights of different hues and different brightnesses during the day. So that is the natural cycle around which the circadian rhythm and a body rhythm operates. Okay, so, and it has been shown, that if you're exposed to a single white light environment spectrum for a prolonged period, for example, UV heavy light in office spaces and factories, and it's been shown to be harmful for physical health as well as mental health. I mean, this is the key thing. I mean, in Canada, you may have this situation where when you don't have daylight or bright light or short days, people get depressed. The big problem, of course, in Scandinavia as well, there's a lot of, winter depression when you don't have enough light, okay? Now, so our ultimate research goal is to have lighting environments which are artificial, but can mimic the natural daylight color and brightness variation to mitigate imbalance in the circadian rhythm is the research goal, it's the ultimate research goal. So smart white lighting is just the start of something where we hopefully can make environments, lighting environments, which are much more human-friendly and customizable, maybe depending on your mood. You can customize your own environment, light environment. And what this technology of quantum dots and what we're showing you is the genesis or the nascent stage of trying to design these types of lighting environments. Okay, now this lighting environment may not just be like this, okay? Does not be lights like this, there could be whole wall lights and so on. And this, what I will show, is another aspect of what we have done, which is a smart textile lighting display. That is, you can create textiles, which are just fabrics or curtains, which will light up. How do you do that? You have fibers which are functionalized. You can functionalize them with quantum dots, for example, and you actually weave these fibers just like you weave a textile, and they become functional fibers. Now, of course, if you want to display, you also need transistors. You may need some sensors, and all these things can be done on fibers. And there's a European program which is called 1D Neon, which is great. And we have this integrated fiber environment, a display, where the lighting aspect comes from quantum dots, which are incorporated into fibers. Okay. So this shows a fiber display. It can be essentially, it's flexible, obviously. It's very large. It can be a whole screen. And they can have a number of devices. They can have RF, that's for communicating, just putting your remote onto it. It can have an RF receiver, which is made by having an antenna, which is silver decorated fibers. A photodetector, if you want that, that is a fiber which has zinc oxide and graphene on it. A touch sensor, which is a biaxial conductor. It's a resistive, again, decorated with silver. A temperature sensor, a biosensor, a supercapacitor for energy. And then, of course, the light emission coming from quantum dots. Okay, so this shows one of these big curtain type displays woven displays, emitting light, depending on here. In this case, this is turned on by taking UV light into the photodetector, which then turns on the display with some pattern, whatever you want. So it gives you a light source capability I talked about, but also there's another aspect where this light source can be coupled to form factors, which are also, very new and revolutionary in terms of active light surfaces. Okay, so with that, I'll come to a summary of my talk. The quantum dots are I hope I've convinced you, are efficient inorganic light conversion materials. They can be utilized in two modes, photoluminescence and electroluminescence. The third one is really crucial, the wet chemical processing, which gives us this choice doing engineering. So the chemistry is perfected to the point that we can actually do engineering. The process is repeatable. You can get quantum dots of a certain size, which will always give you that light emission, and it's scalable. Okay, so without that, there's no engineering. But the chemists have got that bit mastered. And it's an attractive medium, therefore, to explore this smart lighting. And the reason for exploring smart lighting, I told you why we're looking at that. But then there are, of course, other problems as well. I mean, it's not that the research is all done. The whole conversion is not very good. For example, in image sensing and photovoltaics as well. The charge transport, we don't understand completely well. Our modeling can be better. So there are, other research issues as well, which have to be addressed. Then I have to, of course, acknowledge the UK research funding mechanism, the EU, and also Huawei, who supported this research. Okay, with that, thank you very much.
Thank you very much for a very interesting presentation. Some of you know that I'm a spectroscopist. That's what we do for research, and I've certainly seen the light in your presentation. Before we open the seminar to questions, I want to remind you that at 2 o'clock in this room, there's a drop-in session. So if you have any questions, you're welcome to come and ask any questions that you may have, and that's for 2 hours. So thank you again.
Okay, no problem. Yeah. So should I ask any questions now or just in the drop-in session?
By now is meant for the technical talk.
Yeah, sure. Yeah, actually, if you have any questions, please ask me. Go ahead.
It's getting good. So question one, with the indium phosphide, way back then, during the talk, you had a core of zinc sulfur selenide around the indium phosphide.
Yes.
I have two questions. One is, why is that shell around that core? And if you stimulate light emission from the indium phosphide, what happens is that light then travels through what I presume is the shell of the zinc sulfur selenide.
Yeah. So okay, so generally, I mean, that has to have a wider band gap generally than the light. So the light which is emitted in the quantum dot has to go through and out. Okay. But you can get another situation. I mean, I haven't gone through all the other details where the core, the shell actually the lower band gap, and the shell actually takes part in the light emission. There's a whole aspect of that, but I've only talked about that. And then I think the chemistry has been done, I think, empirically to work out the best passivation. Have the transparency and have the best passivation and that's reflected in the photoluminescent quantum yield, which we're getting.
So that's basically what you're trying to
maximize
to improve the quantum yield by fiddling around with the core shell.
Yeah. So the core shell, I mean, that's a huge literature on that. On people, researchers doing the colloidal chemistry. You got to make it, and then working out this is the best combination with that. But the basic one which we used in our light emission, what I showed you in the white, it's a very the base system, which is cadmium selenide with zinc sulfide.
Oh, it was more than that.
Yeah, but it works. and it's scaled, and so so that's why we use that system. And we purchased it. I mean, we didn't synthesize that. That was purchased from a supplier.
And the efficiency of the blue light is lower than that of the red because of thermal recombination or something?
Yeah, I mean, I think it's a good question. I mean, I think the dot is smaller, right? So one way of looking at it is that the surface to volume combination is higher on the blue. And therefore the surface recombination, I think, is still a big problem. Right? And so as you go to smaller and smaller dots, the quantum yield becomes less. So, and then of course, then it's dissipated, it's thermally dissipated, obviously.
Last question. Can you modify the ligands that you use to protect the surface to actually tune the adhesion quality?
In principle, I guess you could do. Yes, but I don't know enough about that actually. I mean, so yeah, but I'm sure in principle.
That's where you have to hire one of Linda's students.
Yeah.
I thought it's just throw the plug in. Right, really?
Thank you for the interesting presentation. I have two questions regarding the white light work. I am wondering, you were doing some work on with machine learning to adjust the width ratio between the different.
That's right.
When we look at the efficiency of the differences between the efficiency from blue to red, there were 1 to 2 order of magnitude difference. And I was interested to see how this can reflect in the different ratios when we want to change the indexes, right?
Yes, yes.
The range for the ratio of the width. This is my first question.
You mean the width, the range, or the weight? Okay, I don't have the display, but essentially though the efficiency is 2 orders of magnitude less, the blue width is compared to the red is about an order of magnitude, so 1 to 10 almost. Okay, between the red, the green, and other two are in between. But your question is right, because that blue efficiency is such, it's not so good. Our LED lights, in terms of getting this hue, the power efficiency is still not good enough. Okay, so if you compare to the LED light which you have at the moment, the electricity to light emission of a commercial LED light is about 40–45%. Okay? In our case, we're most probably down at about 10, between 15 and 20%. So the power efficiency is still not good enough, and that's one of the issues.
And last question is, have you looked at the stability of these devices?
Over long term?
Yeah.
Yes. I mean, I think they've. I mean, okay, it's not our work is not industrialized. Okay, so it's lab. But of course, in the process of making these backlight units for LCDs, they worked out a number of layers for encapsulation, non-reactivity and so on. So it's been commercialized, and we know that the encapsulation and other techniques, I mean, they're there available. So, and the LED backlight unit, I started with that because that is the industrialized technology. And that is available. So we're drawing on that. But of course, what I've shown you is still a lab light, not a commercial light.
Really? Going back, piggybacking off of that question. You showed how you can vary the sort of color temperature with voltage, right? And so I guess as you get sort of more sensitivity for that, you're also at the mercy of your driver and the stability that they can maintain.
So the driver electronics is, I mean, the voltage range is 3 volts to 7 volts.
Right.
So that's okay. You know, that is okay. But the problem is that, I mean, coming back to your, if you've got to have some feedback mechanism where if you're at a certain spot and the light is varying because the efficiency of one of the colors is going down, then you have to feedback and adjust the voltage to try to get back to that point.
Right. So where's the bottleneck? Is it the efficiency of the color conversion or the electronics driving the other?
The efficiency of the color conversion. So, I mean, just as you said, you know, if we go to the very high temperature light, I have to go to 7 volts. And so, and then it's also inefficient in terms of the light efficient, inefficient in terms of the light emission. But if you do the, you know, electric calculation, just, you know, the voltage is high, the current is high, and at those temperatures, the efficiency goes down.
Okay.
So those are the issues. That's not the electronics driving, it's just the actual quantum dot conversion process.
But then when you sort of array that into pixels, then does that sort of scale like an n squared complexity now?
Well, I mean, you've got to have a driver which is local, so it'll be like a pixel driver, right? So it'll be like a display driver. So, and that driver has to go to 7 volts, but it has to give quite high current.
Right.
And so, can that be done with current existing TFT technology, which is on very big displays? Most probably not. IGZO won't give you that. But if you go to laser recrystallized polysilicon, you can most probably do that. So, but that will shrink the light size down. Yeah. So
there are these tricks.
Yeah. So there are many challenges.
Yeah. Thank you.
Any other questions? I got a couple of questions.
Sure.
How small can you make this?
So, I mean, I showed you cadmium selenide, which went down to 2 nanometers. Right, so that's a blue.
So if you do the encapsulation, I mean, we're going back to the discussion we had last night. Can you just swallow the thing and take pictures of?
Well, if you can encapsulate it in a biotech, you know, biocompatible way, yeah, sure. I mean, that's what I said. You know, you can have if you want to do sort of spectrometry inside you, you can have a light source which is small enough and bright enough.
How much power does it take?
Well, it'll take. I guess it'll take watts, right? But you don't want it for a long time, right?
Yeah.
So it depends on the time that you want it for. If it's just a pulsing.
That would
a
be
pulse, pulse.
So, how hot does it get when it, like Willie asked, how hot does it get?
Oh, it gets hot. I mean, if the efficiency is 20%, then 80% of it has to heat, right? So it can get, but it's not very hot, but it's, it does get
So we have to kind of.
I mean, it's like all LEDs, you've got to think about thermal sinking.
Budget.
Yeah, thermal sinking. Yeah, heat sinking.
Oh, I was noticing when you were talking about the actual manufacturing, you were doing each of the colors individually using a stamp process.
Yeah.
Are you assuring we've got proper alignment? Because I imagine you don't really want the mixing very well, but you've got really tight margins there. So how are you avoiding the sliding off and ending up with mixes of colors that you put another way?
Yeah, I think that the features aren't that tight. I mean, they're like, those stripes you saw, that for that display, what you were doing it's essentially tens to hundreds of microns width on the line.
How much space is between each of those?
They're basically about each other, right? Because the PDMS stamp is got a structure which is, it's got a protrusion here, protrusion here. So when they overlie, they're obviously on the edges, they'll merge.
So there is some bleed over.
Yeah. But what we do is that the actual emitting light space, which is pure, is much greater than the mixed stage. So that's what you're relying on there.
I have a very general question. Like you talked about cadmium selenides based polymer. I was wondering how does this fare against carbon quantum dots, like which are environmentally more benign?
Carbon quantum dots. Carbon quantum dots have been used for a number of sort of electronic activity and catalysts and other things like that, right? But for light emission, I don't think they're that good. Okay, so the carbon quantum dot, you'll see a lot of stuff for for chemistry and for catalysis and other things. Carbon quantum dots have been used, but for light emission, they're not particularly particularly good, okay, because carbon, unless you're getting a diamond form, is not really a semiconductor, it's a semi-metal. So you're opening up a gap in a semi-metal, and that is, in terms of light emission, it's not that good. Okay, so that I think is the first order answer to that question. So.
A very interesting question. Any more questions from the audience? Go ahead.
Sir, do you have any reverse device that measure the light instead of generating light?
Yeah. So I didn't go into the top. I mean, I got some slides, but I didn't show that. But you can use it for photodetectors and photovoltaics as well. Okay, so you can absorb the light and then separate the electrons in the holes, and you get a photovoltaic effect. So you can do that with this as well. But the efficiency still is not that good, and there are some other problems of recombination before you separate the electron in the hole. So it's the reverse process. What is good for light emission is not good for photodetection and photovoltaics, because the very fact that they can recombine efficiently means that the moment you generate the electron in the hole pair, before you can separate them out, the probability of recombining is high. So you need to engineer the opposite, somehow getting the electron and separating them out of the quantum dot, or breaking the exciton, as we want to call it, that from a molecular perspective.
Specifically, I'm asking this question because I'm working on metal graphene structures. For example, imagine that we have a graphene phone, and on the graphene surface, we have some metal oxide nanoparticles.
Yeah.
With evenly distributed state. For example, if you use zinc as a metal oxide, maybe we can measure the UV light.
Yes.
And UV and blue at the same wavelengths maybe is important for you. Therefore, why we cannot embed it, some tiny device into your LEDs to measure the critical light, which was, I think, blue.
Yeah. So, for example, what I showed you on the smart textile display, that has one of those. Okay. So it uses a quantum dot light photodetector as well as a light emitter. Okay. So we have a fiber photodetector, which is also based around quantum dots there.
Any more questions? Fascinating.
Okay.
Field.
Okay, I think questions are exhausted.
Yeah. Well, I'm sure people want to get lunch.
Yeah.
But I want to remind you that between 2 and 4 o'clock, Professor Amaratunga will be here to answer any questions that you may have. Scientific, technical. I don't want to open it too much. So thank you. Thank you. Fascinating lecture. Thank you.